and you can get started. Thank you.
Right. Thank you very much, Sam. Thank you for the organization. And as you stated, I'm going to talk about MCMC, and in particular about the Hamilton and Monte Carlo algorithm. Right. So this talk presents a new algorithm that I will try to convince you that it can yield a robust alternative to Hamilton and Monte Carlo. I say alternative, but it's also an extension, simply because Hamilton and Monte Carlo is a particular case of this algorithm. And it's built upon, as you can see, Langevin trajectories that are corrected with a Metropolis type accept reject mechanism. And what we mean here by Langevin trajectories, you might know these under different names, depending on what the literature you've read, or maybe you don't know this process. I'm referring here to the underdamped Langevin process, which has several names, such as kinetic Langevin or second-order Langevin. Or simply Langevin. In molecular dynamics, they use this a lot. And I'm going to start right now. Okay, so this is joint work with Riou-Durand, who is another postdoc from the University of Warwick. And I'm going to split my presentation into three parts. First, I'm going to do a bit of recap about what is Hamilton and Monte Carlo and insist on some problem of robustness of Hamilton and Monte Carlo. What I mean by robustness here is robustness of tuning its parameters. It's quite known that HMC is sensitive to the choice of its parameters, especially the choice of the integration time, which is the length of the trajectories that will be drawn at each iteration of this sampling algorithm, this MCMC algorithm. And we're going to discuss a bit about solutions suggested in the literature to tune its parameters and sublimits and things to tackle. Right, in the second section, I'm going to motivate the study by presenting the Langevin diffusion, also known as underdamped Langevin diffusion, and I'm going to motivate this study compared to another approach suggested in the literature to tackle the problem of robustness when tuning integration time, which is known as randomized HMC. So here, randomized HMC refers to random choice of integration time at each iteration in HMC, and we are going to do some parallel, connect the two approaches to continuous time processes, discuss a bit about theoretical guarantees that are measured by quantitative exponential mixing rates. And in the third part, motivated by this study, we're going to introduce this algorithm, finally, this Metropolis-Adjusted Langevin trajectories, or MOAT algorithm. And I'm going to try to convince you that it can give a robust alternative to HMC. In particular, I'm going to support this algorithm by optimal scaling results and by numerical experiments. Right. I'm very happy to make this talk as interactive as possible. I'm going to do short breaks between the sections. If you want to ask me questions then or after or interrupt me, that's perfectly fine. All right. So let's go. I'd like to start with simply finding notation that will be used during the talk. These are just metrics and norms that I will refer to. And we are going to talk about a particular MCMC algorithm known as Hamiltonian Monte Carlo. Right? So, general goal of MCMC algorithms, I'm sure you all know that it's to sample approximately from the target distribution. Here we are going to assume that this target distribution has density with respect to Lebesgue measure NAD. Right? And this density, we also are going to assume that well, it's positive everywhere, and it is differentiable, and its gradient is Lipschitz smooth. Okay. Right. And so how HMC is built is by combining basically some numerical approximation of dynamics that are defined through an ordinary differential equation and introducing some randomness by drawing some starting velocity by a Gaussian distribution at each iteration. And so first I'm going to describe a bit, recall what are Hamiltonian dynamics, their properties, and then talk a bit about discretization, and then about the algorithm and how it is constructed. So Hamiltonian dynamics are basically defined here by this system of ordinary differential equation that tracks the of position x and a velocity v on an extended space on R2D. Right? And so what happens is that if you start from x0, v0, well, these dynamics will somehow force you to follow the contours of the density on an extended space on R2D. And this density actually boils down to this density pi star here, which is simply the product between the density, target density pi, and a Gaussian density for the velocity. So one property of these dynamics is that they preserve this measure pi star, which is just the product between pi and a Gaussian. And therefore, if you can solve the approximate sampling problem for pi star, you also solve the approximate sampling for pi, because you just have to restrict your attention to the positions, and marginally they will be approximately distributed according to pi. Okay. So these dynamics, they leave pi star invariant. Of course, they are completely deterministic, so it's not yet an ergodic Markov process or any MCMC algorithm, right? Because it's just deterministic, it will just go around and around. So if x0, v0 is distributed according to pi, xtbt will be distributed according to pi, whatever t, positive t you choose. Now, if you want to build a sampling algorithm that will be ergodic, which means that it will converge to the right stationary distribution, well, you need to introduce randomness. Okay. Right. So prior to that, we're going to discretize integrators that have been proposed, and probably the most famous one is known as the leapfrog integrator. It's also known under a different name as the Stormer-Verlet update. And the principle is quite simple. We split here the system of ODE into two parts. We'll first follow the dynamics for the velocity for half a step, then compose with following dynamics of the position for a full step that is guided by this velocity, and then composing again with dynamics of the velocity for half a step, right? So h throughout the talk will be the step size. Okay. And so, well, propose a numerical Hamiltonian trajectory. Well, we compose this update here, a certain number of times, L, that can be chosen to be certain amount of integration and time t divided by the time step h, if you prefer. And we'll compose L times this map theta h, which gives us the deterministic map, which is the F composition of the Stormer-Verlet update. Okay. Right. So built upon this time discretization, the HMC algorithm was introduced in 1987, and its principle is the following. We start from a fresh Gaussian noise at each iteration, fresh Gaussian noise for the velocity. And from this velocity and the current position x, we'll draw a Hamiltonian trajectory, which is here the perfectly deterministic proposal, given x0 and v prime. And we will accept this deterministic Hamiltonian trajectory with certain probability that corresponds to the ratio of densities of the output and the inputs of the trajectory. Okay, so this accept reject mechanism is known as the Metropolis correction. I'm sure you're very all familiar with it. Now, as you can see, there's a last step here, and that can be included or doesn't matter in the algorithm, and it corresponds to a flip of the momentum upon rejection, right? So why? Well, why putting it here? And why does it matter, right? So the answer is it doesn't matter. It's true. It doesn't matter because it's fully refreshed each iteration. Therefore, full refreshments always erase the momentum flips, right? But here I want to illustrate something, which is that you can see HMC as the HMC kernel as a composition of two kernels that both preserves pi star. The first one is a refreshment of the velocity, full refreshment of the velocity, and x does move. Since pi star is marginally distributed according to a Gaussian distribution for the velocity, this kernel leaves pi star invariant. The second one is the composition of these three last steps here, that proposes a deterministic trajectory and then accept or reject it with a certain type of metropolis correction that actually takes advantage of the fact that we have some particular structure of this proposal here. There is one property of Hamiltonian dynamics, in addition to the fact that it leaves pi-star invariant. One property of the dynamics is that they are so-called time reversible, right? So what it means is that going forward and then flipping the velocity and following the same dynamics actually makes you going back to your original point, right? So essentially going backward is the same as going forward, it's just up to a flip of the velocity, right? And so this notion of time reversibility has particular impact in MCMC, and this notion should be connected to something that we know it's referred in the MCMC literature as skew reversibility or skew detail balance. So essentially, it's just as detail balance, but there is a composition with an involution, and this involution here is a flip of the velocity. So you can see it like you have, let's say, a kernel P continuous time process with, let's say, a kernel PT. You find time discretization, that is PH if you want. And what you'll do is that, well, PH is not reversible with respect to pi. PT is not reversible with respect to pi, but there is a particular structure which implies that if you compose a flip of the velocity with this PT, it becomes reversible with respect to pi. And so now if you want to use metropolis correction to compensate from the numerical error, what you'll do is you write PH as flip times the flip times PH and apply the metropolis correction only on the two last kernels, right? And that's why, in few words, there are some flips that arise from rejection. Okay, so why talking about this for 2 minutes if it's going to be erased? You might ask. Well, that's a good question. Well, the answer is that a few years later, in 1991, Horowitz introduced a generalization of this algorithm known as GHMC that involves an additional parameter. And this additional parameter here is the so-called persistence parameter alpha. And you can see here that in the statement of this algorithm, the only difference with the standard HMC algorithm is that now we allow for partial momentum refreshment. Right? So in the second step here, when alpha is equal to 0, we recover standard HMC, we fully refresh the velocity. As soon as alpha is strictly positive, refreshments become partial and more partial as alpha gets closer and closer to 1. Right? So this has advantages and drawbacks, right? One advantage is that one of the main motivations for introducing this generalization was to introduce some persistence in successive trajectories. And in particular, if you choose alpha quite close to 1 in the way that we will describe later on, actually this algorithm for small time step can approximate the standard Langevin diffusion that we will call Langevin diffusion. Right, one drawback here is that, well, as soon as alpha is strictly positive, well, partial momentum refreshments are do not allow for full erasement of the flips. And it means that whenever there is a rejection, the trajectories will just backtrack on themselves, right? Which is really opposite of what we want. And so probably for this reason, this algorithm, I think it's fair to say, received limited interest compared to the standard HMC algorithm. Nevertheless, there were many methodological variations that really aim to propose some solutions to mitigate the impact of the flips. Right? So there's a whole branch of methods that use so-called delayed rejection methods to try avoiding these rejections and therefore the flips at the cost of a higher computational complexity. And so there is another trade-off to solve with these methods. There is also a more recent approach proposed by platform Neil in 2020 that tries to do some slice sampling with the uniform distribution that will determine the outcome of the accept reject mechanism, try to cluster the flips in a short period of time such that it's not too avoids really diffusive behavior, or at least the diffusive behavior is clustered. There are several approaches that really aims to try to mitigate the negative impact of the flips on performance of this algorithm. So here we are not going to compare to these approaches, but we are going to keep in mind this problem for GHMC and come back to it later. Okay. Now let's discuss a bit about solutions that have been proposed in the literature to tune the parameters of HMC. So we've talked a bit about the problem of GHMC. So now let's remove the problem and just assume that alpha is equal to 0. We recover standard HMC, full refreshments, and we still want to choose time step h and the integration time t. So the first result that I'm going to discuss is a result about the scaling limits of the HMC algorithm corrected by this accept reject mechanism. Right? And so one motivation of these scaling limits is to be able to say something about how to choose a time step to avoid getting a trivial acceptance rate that is either too close to 0 or too close to 1. Okay. Right. So these works have been conducted first for random walk, then for the Mala algorithm, and then for HMC in 2013. I'm going simply to describe here in a few words how to interpret it. Well, here there is an assumption, as you can see, which is quite a strong assumption because it assumes that the potential function writes as a sum of individual functions, which boils down to assuming that the target distribution is a product form, right? So all the components are independent. Of course, this is not realistic, but it allows for a neat mathematical framework that enables the study of the asymptotic of the acceptance rate as dimension goes to infinity. Right? And so as dimension goes to infinity, the largest time step that you can choose to get an asymptotic acceptance rate that will not vanish to 0 and get your algorithm stuck is the dimension to the -1/4 scale. Right? So if you choose time step to decay to 0 at this rate, then you obtain an asymptotic acceptance rate that will be non-trivial, and the framework is sufficiently neat to allow for an explicit optimization of the constant in front, L, here, with respect to several measures of efficiency, such as the expected square jump distance, for instance. And it gives us, in addition to this scaling information, it gives us also nice tuning guidelines because it shows us that the asymptotically the best time step is such that the corresponding acceptance rate should be around 65%. So it's very easy to monitor. This nice tuning guideline that we can use everywhere, and that's great because that gives us simple rule to choose this time step. Right? In addition, it gives us some information about the number of gradient evaluation required to approximate a certain amount of integration time when you're trying to approximate these trajectories. So, of course, an optimistic framework, it's useful information because here it means that we can't really hope to compute less than dimension to the 1/4 gradient evaluations to be able to reach a certain amount of integration time. Okay. All right. Second result that I'm going to discuss a bit is actually a study about an adaptive tuning algorithm quite well known by now, which is known as the no U-turn sampler. So I'm not going to focus too much about the details of the adaptive tuning mechanism. I'm simply going to describe here the tool they use, loosely speaking, to achieve this goal. So the first observation is that Hamiltonian dynamics, okay, they are the solution of a certain ODE, and therefore we can also compute the dynamics of the square norm between xt and x0, right? And these dynamics are driven, right? It will increase if this scalar product is positive and decrease if this scalar product is negative, right? So if somehow we would like to build an algorithm that will prioritize in some sense points that are further away in the hope of reducing the correlations, well, one intuitive idea would be to follow these dynamics until this so-called no U-turn criterion is met, and somehow ensure that the algorithm will build has the right stationary distribution, which is not trivial. Right? So I'm not going to go into this detail here, but somehow I'm going to illustrate here that, well, these algorithms, and so this is one example. There have been other adaptive tuning solutions proposed, and they received a lot of interest because they provide black box tuning for the integration MT, which, and we know that HMC is quite sensitive to this choice of integration time. Here, if we are happy with optimizing or maximizing the jump distance, the Euclidean jump distance in expectation, then this principle makes sense. Right. Here, I'm going to point out the limits and form it as a question, which is not really inherent to adaptive tuning solutions, more generally about a fixed time strategy for HMC. And it will allow us to motivate the study that we will present. Okay. So here, if we consider maximizing this expected square jump distance measured by the Euclidean metric, well, actually, the Euclidean metric, it might be that there is one value of t that maximizes this expected square jump distance, but even if there is, there are actually a lot of situations where we can have arbitrarily bad mixing for a given component, say. And this is actually well known for HMC. And we don't have to go very far to see this type of problems appearing. In particular, here we illustrate these problems of a fixed choice of integration time for HMC on heterogeneous Gaussian. Right? So it's just a simple Gaussian distributions with different scales, right? Okay. And so we're going to plot here the so-called autocorrelation functions, or ACF, that correspond to the correlation between the output of a trajectory and the input of trajectory. Right? So we can interpret these rho I of t as the first order autocorrelations of each component I between 1 and d. Right? So we want these to be as close as 0 as possible to be able to sample, to get MCMC samples that are as uncorrelated as possible. Okay. And so if we plot all these ACFs, you can see here on the right-hand side for the Gaussian case, everything's explicit. It's nice. We get actually formulas that boils down to simple cosinus function with different bandwidth. And the first remark is that, well, if you have heterogeneity of scales, it means that it will be quite hard to find the value of t that will be able to control all these ACFs at once. In particular, if you look at the worst ACF, which is this map, this maximum absolute value of this rho I of t, it's a map with respect to t that can be arbitrarily erratic and arbitrarily close to 1, as it's illustrated on plot here. And so that's a problem, right? Because there's a lot of situations, if we think about approximating posterior distribution in the Bayesian inference problem, where we are very much interested in all the marginals, and we would like to get some robust guarantees, some way to ensure that we get good mixing for all the components and not just globally in terms of expected square jump distance. Right. So the main solution suggested in the literature to tackle this problem consists on choosing these integration times at random. Okay. And so what is the motivation? The motivation here from this plot is quite clear, is that somehow if we can well, choose t at random, instead of obtaining a fixed bunch of ACFs for each component, we will get some expected ACFs, and we induce some smoothing and averaging effects. Right? So there are many possible choices of distribution for drawing t at each iteration. Here we point out to a reference that studied the choice of the exponential distribution from Bouabi and Sansana in 2017, but this idea is not new somehow, and you can find some other study with respect to the uniform distribution already in the book of Radford-Neal in 2011. It's already a bit discussed. Of course, knowledge has been improved and improved over the years. And so, but all of these strategies, they rely on similar principle. And well, to just to point out for the choice of the exponential distribution, somehow what you get in the end is a uniform bound over all these ACFs that now decays with respect to the average integration time in a monotonic way, right? So remember here, the average, the expectation of the exponential distribution is the inverse of its parameters here. And as you can see here, well, as this parameter, as this inverse of the parameter goes to infinity, we recover something that decays to zero. Okay. So this gives us somehow a way to tune the average integration time instead of tuning the integration time. That enables robustness, robustness of tuning the integration time to ensure control of all the ACFs at once. Okay. Right. So do you have any questions before I motivate the study of the Langevin diffusion and then introduce the algorithm we studied? Nope. Okay. So now we study here the choice of the Langevin diffusion, also known as second order Langevin or unbound Langevin, kinetic Langevin. And it's a diffusion process here that lives on the same space, this extended space, R2D. It's guided by velocity v. And as you can see here, it can be interpreted as Hamiltonian dynamics, but with an additional component here that corresponds to continuous refreshment of the momentum induced by Brownian motion WT. Right? So the second part here defines well, an Einstein-Lebesgue process for the velocity v, and there is one parameter gamma that controls how fast this process will mix. And this this parameter here is known also as damping parameter of friction. And whatever choice of damping or friction, well, these dynamics preserve the same invariant measure pi star, right? So main difference with the Hamiltonian dynamics is that now the trajectories are random. It's a stochastic differential equation that allows for ergodicity of trajectories that will be drawn from this SDE. And the first question we ask ourselves is, can this process somehow yield an alternative to introduce sufficient randomness in the trajectories to ensure robustness of tuning, right? In a similar way as we can get for randomizations. And we look here at the same running example, this Gaussian with heterogeneity of scales. First, we consider the case where all the scales are the same. So there is no heterogeneity, it's perfectly isotropic. You can think of it as a one-dimensional problem if you want. And so we fix all these sigma I equal to 1, and we just represent various choices of friction, and we look at this first-order autocorrelation. Right? So this first-order autocorrelation can be plotted as a function of the time, the integration time we'll choose in the algorithm. And as you can see here, there are different behaviors depending on the choice of damping parameter. So when damping is equal to 0, we recover perfectly deterministic Hamiltonian trajectories, and therefore we simply recover the cosine function. Right. And so now, as you can see, if you have a value of friction that is between 0 and 2 here, you get some oscillatory behavior that will vanish eventually towards 0. And if you are above 2, you get some monotonic decay towards 0. Somehow there is a critical choice of damping that separates these two regimes that will be called underdamped regime over the threshold and overdamped regime above the threshold. And this critical choice of damping, actually, it's quite known for the Langevin diffusion, that it optimizes the long-term exponential rate of convergence towards 0. Okay. So, well, yeah, it's the best long-term convergence if we choose gamma equal 2. It's true, but of course, if you want to obtain correlation close to 0 as fast as possible, well, the choice gamma equal to 0 is the best if you are able really to tune it perfectly. Because if you are able to choose t equal pi over 2 here, you get correlation equals 0, and you get perfectly uncorrelated samples faster than any other choice of friction. Right? Remember that the computational costs of the algorithm can be measured here by the number of gradient evaluation that we are going to need to compute. And this number of steps is roughly the integration time divided by the time step, right? So for a fixed time step, the computational complexity is proportional with this integration and t. Okay. Right, so that's okay. So that's actually quite known. Now we are going to look at the similar ACFs, but in a different setting. And now we are going to fix the friction, the value of the friction, and introduce heterogeneity of scales again. And here what happens. And so on the left-hand side, you know this plot is for HMC, gamma equals 0, and the right-hand side is for this critical choice of damping. And we superpose now all these ACFs for various scales. And one thing that we can remark here is that on the right-hand side, all the components, all the ACFs corresponding to components that have a smaller scale, that's the reference scale chosen sigma equal 1 here. Actually, they get ACFs that are all dominated by this reference scale. So this gives us actually a nice tuning rule for ensuring control of the worst ACF, which relies on choosing this damping parameter to be the critical choice of damping for the larger scale. And when we do that, it's as if we were just assuming that the reference scale is the largest one, and we get a uniform bound on all these ACFs. And as you can see, the resulting bound here decays exponentially fast with the integration time, and does not require randomization of the choice of t. So we recover a similar uniform control over all the ACFs, and that decays in a monotonic way with respect to t. Right, so now I'm going to apologize for the next two slides because they contain a little bit of formulas. And the only goal of these two slides is to make a quick theoretical connection between the randomized HMC continuous time process and the Langevin diffusion continuous time process. Okay, that's the only goal here. And the goal of this study will motivate the construction and the numerical investigation and the theoretical investigation of the algorithm we propose. So here, the randomized HMC continuous time process can be parameterized by two things here. The first one is the parameter lambda that measures the intensity of refreshment of a Poisson process here that will drive the momentum flips that will arise. Okay. So basically what it does is that it follows perfect Einstein dynamics, and at some point that are driven by this Poisson process with intensity lambda, it will perform some refreshment, discrete refreshment. And well, we can choose to get some partial refreshments by using this persistence parameter alpha that we already know. Okay, so it's the same parameter alpha. Now there is this additional parameter that controls how fast this refreshment occurs. And on the right-hand side, we get, remember, we have this friction or damping parameter for the Langevin diffusion gamma that controls how fast the continuous refreshment will occur. Actually, these two processes are quite connected. They are quite close to each other because they are built upon similar stones. When we look at the infinitesimal generators, which somehow characterize the distribution of the stochastic process, we can see that the generator of randomized HMC and the Langevin diffusion are actually built upon three stones, one of them being common, which is the generator of Hamiltonian dynamics. And the difference comes from two different sources of refreshment. So the first one contains refreshment induced by a Poisson process with certain intensity lambda, right? And the refreshments are involve certain partial parameter of persistence, sorry, alpha. Okay. And the second one basically is dictated by continuous refreshment of the velocity with certain damping parameter gamma. Okay. Right. And so this first result here is a statement that somehow claims that the two processes can actually be arbitrarily close to one each other when you consider partial momentum refreshment that becomes more and more frequent and partial for randomization C. So you think about randomization C with this Poisson process with an intensity lambda and a persistence parameter alpha. If alpha converges to 1, refreshment becomes more and more partial. And if you choose lambda that goes to infinity at this rate, they become more, they happen more and more often. And by doing that at a certain rate, you actually converge to the kinetic Langevin diffusion. Right. Okay, so in other words, Langevin diffusion can be seen as a limit of randomization C if you get partial and frequent refreshment. That's it. Right. So there's an intuitive explanation for it. And then we can ask ourselves, well, in terms of convergence, like it's a theoretical abstract result, but it's in terms of convergence of this stochastic process, continuous time stochastic process, can we say something about their convergence rate? And so there have been recent works about both continuous time processes actually to get some quantitative rates of mixing for this process, right? So we study here exponential convergence towards the stationary distribution, but in a particular framework here that allows to get quantitative rates, right? And this framework here is the framework of strongly log concave targets. So that's the assumption on the left-hand side here. And the right-hand side boils down to assuming that the gradient of the potential is Lipschitz smooth, which we already assumed before. Under this assumption, as you can see here, there are some convergence towards the invariant measure pi at an exponential rate, and the rate is measured by this quantity R. Right? And as you can see here, the rate of convergence, which is the best, now these are upper bounds, but it's the best upper bound proven so far. So that's one of our results. Actually is optimized for a value of alpha that converges to 1, while the corresponding intensity of refreshments converges to infinity at a particular rate, which is the same rate as described in the last slide. So how to interpret this result? Well, basically, if you just in a few words, if you want someone to optimize the best upper bounds we get so far on these mixing rates, with both respect to the Versailles distance and the L2 norm, and want to optimize this rate for randomization C with respect to its parameters, which are the intensity lambda of refreshment and the persistence parameter alpha, somehow the optimal solution when looking at optimizing this upper bound pushes you towards the kinetic Langevin diffusion. So that's the take-home message. Right, so this result can be, so it's built upon previous results, and it can be seen as a continuous interpolation, in particular of results from George Degmanidis and for the randomization process, and results that we obtained with Lionel during my thesis for the kinetic Langevin diffusion. So take a message, I guess, here is that the Langevin diffusion can be seen, well, first as a limit of randomization C, but that also achieves the fastest exponential mixing rate, or is best upper bound so far proven for strongly log concave targets. And so this result in particular is true, it's just a theoretical result, but it motivates the study and the construction of a sampling algorithm directly built upon Langevin trajectories to propose an alternative to this randomization of the integration time within HMC. Right. So now I'm going to introduce this algorithm at last, unless you have questions before. Fair enough. Right. So to introduce this algorithm that, as I said, can be seen as an extension of HMC, we first are going to discuss about the time discretization of the Langevin diffusion we're going to use. And there is not a lot to say here because it's directly built upon the leapfrog integrator that we described at the beginning of the talk. And as you can see here, these 3 last steps in the middle, they simply correspond to this leapfrog integrator. Right? And somehow this leapfrog integrator is composed by some partial momentum refreshments of the velocity here with a certain quantity here, alpha, that is no longer a free parameter, but is fixed by the time step and the friction gamma. Right? So in particular, when the time step gets closer and closer to 0, the quantity alpha gets closer and closer to 1, the refreshment becomes more and more partial. Right? In particular, if you take gamma equals 0, well, you just get like no refreshment at all, and therefore you just recover the leapfrog integrator. So we'll call this, we'll somehow characterize this update through a Markov kernel, QH gamma. Right? And so this Markov kernel, as you can see, if gamma is equal to 0, it's just a direct mass, it's just deterministic leapfrog, right? If gamma is strictly positive now, it has a density with respect to Leibniz measure, right, on R2D. And so we will now build this algorithm by proposing, instead of proposing numerical Hamilton trajectory, the only thing that we will do is we will propose numerical Langevin trajectory for L steps by composing this kernel L times. Okay, and so here is the algorithm. As you can see, it's very similar in statement, its formulation as the standard HMC algorithm. And here, in addition to choosing time-step integration time, there is also this damping of friction parameter to choose. Okay. In particular, when gamma is equal to 0, this algorithm boils down to the HMC algorithm. Okay. So how does it work? Well, at each iteration, we start, just as for HMC, we start from a fresh Gaussian noise for the velocity. And conditionally on this noise and on the current position, we will propose a numerical Langevin trajectory from this Markov kernel composed L times. Right? So, as I said, when gamma is equal to 0, this is just the leapfrog integrator. It boils down to HMC. And in that case, the acceptance probability is just the left-hand side of this formula. As soon as gamma is positive, what happens is that this kernel now has density with respect to Lebesgue measure R2D that will denote small qh gamma. And it turns out that if you multiply this ratio by the ratio of these densities, which are densities over the space of trajectories, where on the denominator we get density of the forward trajectory, and on the numerator we get density of the backward trajectory with flip momentums, we actually obtain an acceptance rate that characterizes the standard Metropolis correction. And when composed with this flip of the momentum upon rejection, forms this kernel here that leaves the stationary distribution invariant. Right? So just as for HMC, this last step is not needed in the algorithm because, well, the velocity is refreshed at each new trajectory, which is quite a major difference with the GHMC algorithm that can also approximate the kinetic Langevin diffusion, but suffers from momentum flips upon rejection. Right? So that's why we argue that this Metropolis correction is quite interesting, and so it's a new approach that focuses on Metropolis whole trajectories in a way that can be argued to be neat in the sense that they fully refresh the momentum, and therefore they avoid these momentum flips. In particular, the difference with the GHMC approach that aims to mimic the kinetic Langevin diffusion is that here there is an additional degree of freedom, which is the length of the trajectories, its integration MT, which can be chosen directly by the user. We also highlight here that if you choose positive damping, well, we have somehow illustrated that positive damping can enable robustness of tuning the integration time, because you can get some uniform control over all the ACFs at once, which you can't really do for gamma is equal to 0. In particular, if you get a positive friction, just to understand a bit how the algorithm works, is that, well, you now propose trajectories that are ergodic, right? So if you propose longer and longer trajectory, what will happen somehow is, well, it will cost you more in terms of running time, that's sure. But since these trajectories are now ergodic, what you get is decorrelation as time goes to infinity. Right? In particular, you cannot suffer anymore from so-called U-turn problems for HMC, which sometimes you can just waste a lot of computational resources and just come back to your original point with high correlation. Finally, we support this algorithm with a study of its scaling limits, and we recover actually very similar guarantees to HMC without additional assumptions. And this is the point of this slide here. Right, so as you can see, that's the same framework. We look at how to choose the time step for the product form assumption here in order to get non-trivial asymptotic acceptance rates, and the rate obtained is the same, the dimension to the -1/4. And actually, this is a direct consequence of using the leapfrog integrator. What we kind of show here in this result and in the corresponding section in the preprint is that somehow these properties inherits for the choice of the leapfrog integrator, and that the partial momentum refreshment does not really play a role in the numerical error observed. Somehow it can be interpreted as a sum of local energy difference incurred by the leapfrog integrator, which really shows that it only captures the error of approximating the Hamiltonian parts of the Langevin trajectory. And so for any choice of friction, what we obtain here is basically an extension of the results of Berescos and Cothos, which states that we need dimension to the 1/4 gradient evaluations to approximate certain integration time, and gives us similar nice tuning guidelines to choose the time step, whatever is the friction. Finally, we support this algorithm by numerical investigations. So in the paper, we also look at examples beyond the Gaussian framework. Here, we are just going to take the same running example, but we look also a bit about strongly concave targets and also about slightly heavier tail targets. But so here, just to simplify, here for the same running example, we illustrate what happens when choosing different methods, when looking at this mode algorithm compared to the randomized HMC with full refreshments and to the standard HMC. So the first thing here is probably just to understand, to look at what is plotted, right? So there are two plots. On the left-hand side is a plot about measuring the efficiency for estimating the mean of this distribution for each component, right? And on the right-hand side is for estimating the variance for each component. And the measure of efficiency, as you can see, here is quite a conservative one, because we look at the worst effective sample size that is normalized per the integration time to yield the sensible measure of efficiency, right? So why the worst ESS? Well, because it directly relates to this problem of controlling all the ACFs at once that we illustrated a few slides ago. And there are four different curves, as you can see, right? So the dotted gray line here is a bit particular. It simply corresponds to what HMC achieves on perfectly isotropic targets, right? So you can think about this, if you prefer, as like if it was perfectly preconditioned, perfect Gaussian, perfect. I mean, you can't really hope for best, right? And so, as you can see, well, and when estimating the mean and variance, there are some discrepancy for integration times that are close to pi, because you get quite antithetic behavior. You propose x0, then minus x0, then x0, minus x0. So the asymptotic variance just goes to 0. Of course, it's quite suboptimal when estimating the square function. Right, and the three other curves, they really look at the problem of heterogeneity of scales. Right? So we introduce heterogeneity of scales here in a way that somehow such that the condition number scales linearly with dimension. And somehow the three curves here, the pink being randomized HMC, the blue being MOLT, and the green being standard HMC. You can see that, well, the two first ones are much more robust to heterogeneity of scales. Right? And actually, these two curves, they don't move when you plot these, when you increase dimension for this framework. Right? Because they correspond to basically the ESS corresponding to the larger scale, right? Which is taken as a reference. And well, for HMC, it's not the case. And actually, we just illustrate here what happens for dimension equal 50, so condition number equal 50. But of course, if you increase dimension, well, these curves becomes more and more erratic and close to 0. Right? That's what happens. And so the two robust methods here are the MOLT algorithm we propose and the randomized HMC with full refreshments in pink. And you can see that a small variation of integration time does not yield big variation, even for the worst ESS among all the components. Though there are some discrepancies when estimating the mean or when estimating the variance, right? When estimating the mean, what happens is that randomization seems to perform better in terms of what ESS than MOLT, whereas this order is reversed. MOLT seems to perform better than randomized HMC for estimating the square. We are going to illustrate this actually more generally for this last slide here, where the problem is quite similar. The only difference here is that now we fix the step size, right? And we choose a step size such that we follow the tuning guidelines, right? The optimal scaling guidelines, why not? So we look at a fixed choice of step size that's such that we obtain acceptance rates that are either close or slightly above 65%. And we ask ourselves the question, well, in practice, if I want to choose the number of steps L to obtain relatively good efficiency for every function, how can I do? So one way to do it, one proxy to do it, is to look at the worst efficiency between estimating the mean and estimating the square. That's what we did here in this simulation. And we also computed the corresponding worst ESS for various odd and even functions. So these ESS are all like just normalized per quadrant evaluations, so everything makes sense. And well, what happens here somehow, so if we look at what HMC does, if we want to optimize somehow L to obtain good efficiency for every function, what happens is actually the best choice of L in this example is L equal 1. There is no, in this particular example, choice of L strictly greater than 1 that achieves non-negligible worst ESS for estimating the square. And this is directly due to the fact that this second function is very, very erratic. If you introduce some discretization, then it's very unlikely that you get just on top of the spike. And so we illustrate still what happens for L equals 3 just for an illustration. But so the best choice for HMC is just Mala if you look at this worst efficiency between estimating the mean and the square. Whereas for both MOLT and randomized HMC, well, you can get some robust efficiencies and decent efficiencies for every function, even when looking at the worst ESS of all the components. And this is illustrated here, where somehow we recover a similar discrepancy where randomized HMC seems to perform better than MOLT for odd functions, whereas MOLT seems to perform better than randomized HMC for even functions. Although the difference between the two is still within factor 2p. Right? So, well, that's about it. Just to wrap up, we introduced a study of this kinetic Langevin diffusion, and we first studied from a continuous time perspective and presented as a limit of the randomized HMC continuous time process that achieves the best upper bound in terms of exponential mixing rates among strongly concave targets. Right? We use this somehow theoretical abstract result as an argument to motivate our study. And we also illustrate that the positive choice of damping enables control of the worst ACF and therefore allows for robustness of tuning the integration time. We present this MOLT algorithm as a neat Metropolis correction for approximating Langevin trajectories where the length of the trajectories here can be chosen by the user, which is not the case for GHMC, and for which momentum flips can be fully erased by refreshments, which is also not the case for GHMC. Finally, we support this algorithm by a theoretical investigation of the scaling limits and recover similar results as for HMC, in particular the dimension to the one for scaling and the tuning guidelines, whatever friction we choose without additional assumptions. We have several paths we are quite interested continuing investigating, and we are very open to discussions about possible collaborations if there's something that comes pop up in mind. And in particular, so I'm just going to briefly mention some of these. We are quite interested, obviously, on the adaptive tuning problem for these parameters in order to provide some competitive algorithms compared to adaptive tuning solutions for HMC. We are currently developing a package that is already accessible on my website. We are hoping to submit it to CRAN in a few, I don't know, hopefully weeks, months, right? But it's already accessible to anyone. And we are looking also for further comparisons, both from a theoretical and numerical perspective between modes and variations of HMC. I'm very happy to answer any questions you have, and thank you very much for your attention. Thanks.